Now, as you are doing a literature review, you will find that there are 3 tracks in which, at least 3 different tracks in which the multiscale analysis can be categorized into. One is the signal analysis itself, right, where you are looking at what is the frequency content and all of that. Then you have what are known as feature extractions, where looking features in the time frequency plane. Does this, is there a particular oscillation that I am looking at, or is there a particular shape in case of image analysis and so on, again in the time scale or the time frequency plane. And the third one being systems analysis. No signal comes out without any system. So, there is always a system that is generating the signal. If I am looking at more than one signal, let us say 2 signals, then there is a system that relates probably these 2 signals, and I am interested in modeling that system which connects these 2 signals or 2 or more signals. Sorry, that is where you will find multiscale systems theory predominantly, where people talk of wave nets and all of that. So, there are these 3 tracks. Of course, there are other kinds of tracks which I have left out. As I said, we are predominantly in signal analysis, and in image analysis you will find a few more tracks as well, right. We are primarily going to focus on signal analysis and feature extraction and leave out the modeling part, because that requires more topics, advanced foundations and so on. So, let me quickly give you a feel of what Fourier transforms, why the tools are necessary, and what we have qualitatively talked about earlier, that Fourier transforms are unable to give you the local features. I have a simple example for you here. On the left you see 2 signals where I have 2 sine waves of 2 different frequencies, but switched in terms they are occurring in series, but the order is switched to give you a feel of what Fourier transform cannot do. So, on the top you have the time series, and on the bottom, in the bottom panel you have the spectra, which again which has frequency on the x axis and power on the y axis. It is essentially telling you how much each frequency component has contributed to the overall power of the signal. We keep using these terms power and energy, we will give definitions later on. So, if I look at the spectral plots, we are not able to distinguish between these 2 signals, because what has happened is we have thrown out what is known as a phase information, and typically it is hard to use the phase information because of noise and other reasons. Normally we work with the spectra, and the spectral density is unable to get you the time features of the signal. That is, it is unable to tell you which frequency occurred first and which occurred later. There is another signal, there is another example that I would like to give you, which is a very classic example that is used in testing the ability of multiscale analysis tools, which is a sine wave corrupted with an impulse. And here I have the impulse location being changed. First of all, it's the Fourier analysis will not be able to tell you anyway when the impulse occurred, but just to show you that point, I have just shifted the impulse in both these signals, and you can see that the spectrum remains more or less invariant to the location of the impulse, and that is what it is. The spectrum is invariant to the occurrence of the features in the signal. In fact, this is an acid test for most multiscale analysis tools, where you have sine wave that is persistent throughout in time, but highly localized in frequency. It has a single peak in frequency, whereas you have an impulse which is highly localized in time, but we know from the Fourier analysis that its spectrum is broadband, right. It is spread throughout. So, there are actually 2 extremes that are present in a signal, and if your tool is able to pick out these 2 extremes without much user intervention, then it is a very nice tool, right. Now, the prime reason why Fourier analysis is unable to extract the local features is the building blocks, or you can say the analyzing functions, which are the complex sinusoids, are spread throughout the time. So, that is the main point, and the main message therefore we should take from here is, if I want to capture local features in time, I need basis functions that are highly localized in time, and that is the basic effort in short time Fourier transform. But before we even talk about any technique, we should understand that there are fundamental limitations in time frequency analysis because of the duration bandwidth principle, which says that I cannot obtain the local information in time and frequency with arbitrary fineness. If I try to capture the local features in time, I will have to sacrifice the information on the local features in frequency, and that is the trade off with in which that all these tools work. Fourier analysis actually takes the extreme trade off, and the time series that you have is on one end, on the other end, where you have very nice information in time by virtue of sampling, whereas with Fourier analysis you have very fine information or localization in frequency by virtue of the transform itself, but it loses out on the local information in time. Short time Fourier transform and wavelet analysis and even Wigner-Ville, they are all in some sense or the other governed by this duration bandwidth principle. The other limitation is when I add up spectra. So, earlier you saw that the signal was made up of two components at least. When you look at the spectrum of this added signals, they are not going to be, the spectrum is not going to be the sum of the spectrum of the individual ones. There are going to be interference terms that are going to generate spurious features in your spectrum, and that is another limitation in time frequency analysis. So, predominantly there are two approaches. One is the classical Fourier route, and then you make changes to that, that is the short time Fourier transform and so on. Then you have the multi-scale analysis route, where you recall the relation between scale and frequency. What you do is you break up the signal into different scales from coarse to fine scales using wavelet analysis, and that is what wavelet transforms do for you. There is a third approach, which is, although I have said two here, the scale approach and the frequency approach are more or less the same. So, the second approach, so to speak, is the approach of the instantaneous frequency, where you think of a function of frequency that changes with time. So, instead of analyzing with the basis function that has fixed frequency at all times, which is what Fourier does, you can think of breaking up the signal into components that have frequencies changing with time, and this was the basic idea in Wille's analysis, and that followed Wigner's work. And then more recently the empirical mode decompression also follows this approach. We will study both these approaches fairly at length. So, just to conclude the talk, I will give you a feel of what short time Fourier transform and Wigner-Ville distributions do for you. In the second part, we will look at wavelet analysis. So, the short time Fourier transform is nothing but a variant of the Fourier transform. It is a natural idea. We have identified the problem with Fourier analysis. The analyzing functions exist over the entire time plane, whereas if I want to get local features, I need this analyzing function to be of finite length. So, what I am going to do is I am going to clip the sinusoid, or what I am going to do is I am going to segment the signal. Either way, either perspective is all right. And the expression here, which we are not going to discuss too much in detail, tells you that either that the signal is being clipped with the help of this so called window function, or you can say that the signal is being analyzed by what is known as a clipped sinusoid. This window function is responsible for clipping either the segment or the signal or the sinusoid itself, whichever way you look at it, and Tc refers to the center of the window in time, and omega also refers to the center frequency. So, let us look at what I get from so called spectrogram. The definition that I have given in the top is for the short time Fourier transform. Spectrogram is simply computed as magnitude square. Now, just for the illustration, I have taken up the same signal that we have seen earlier. The spectrogram is able to clearly tell me that there are two frequencies in the signal located over different time intervals. Fourier analysis tells me simply that there are two frequencies, but now the spectrogram is able to get me the local information in time, but of course, there are certain limitations to which to this technique, but by and large it is a major improvement over the Fourier analysis or the spectral analysis. Likewise, here I am able to locate the existence of an impulse in that is buried in the sine wave at more or less the appropriate location. Notice that we are unable to pinpoint the location of the impulse, right, because of the duration bandwidth principle. And likewise, for the left plot, I am not able to say confidently that these are the two frequencies that are present in the signal. There is some smearing of the energy, so that we say that there is this localization in frequency is lost because I am trying to get the local features in time. That is the duration bandwidth principle working for you behind the curtains. And the Wigner-Ville distribution takes, as I said, a different route where it does not work with a transform, directly computes energy density, and the expression, mathematical expression right now, the details of it are not so important, but the only point that I want to make with this expression is you can think of Wigner-Ville distribution as being working with what is known as an adaptive basis. In Fourier analysis and wavelet analysis, we use what are known as fixed bases, fixed analyzing functions. I know what these analyzing functions are, and therefore I know the properties of the broken up segments. I know exactly what the properties of the individual segments are as a consequence. But there is also another route to signal analysis where I do not use the analyzing, I do not choose the analyzing functions a priori. I will wait for the signal to arrive and then determine how to break up the signal, right. That approach is called an adaptive basis approach, which has numerous advantages over fixed basis, because in fixed basis you are always imagining signals to be made up of components that you have pre-imagined. That is not necessarily the case, right. For example, if I have a signal such as this, where it is inactive for a while and then it oscillates for a while and then goes back to 0. Suppose this is a signal that you are analyzing and you did not know that exactly this is what existed, then what would happen is, if you are performing a Fourier analysis or even a wavelet analysis, well, let us talk about Fourier analysis. What Fourier assumes is that this 0, that is no activity region, is made up of several sine waves, which are the analyzing functions, cancelling and adding and cancelling each other, right. And that is not the case, because simply there is no activity. You can't imagine that that this is how the signal would have been generated. It is simply like saying 0 can be 1 minus 1, can be 2 minus 2, can be 100 minus 100, or 0 itself, right. So 0 has to be treated as 0 rather than imagining it to be 1 minus 1 and so on. And that is what happens when you have fixed basis, because you have already kept biased yourself towards a certain way of synthesize of the way the signal has been synthesized. Whereas with adaptive basis, you look at a signal and say no, that these must have been the basis that would have generated a signal, and that is what exactly Wigner does for you. So to give you a feel of what Wigner-Ville distribution does for you, again I have the same signal here. Now if you just compare this plot with the spectrogram, there is a very fine localization of the energy in frequency. Once again we have frequency on the y axis and of course time as well, but there is a certain middle term that is appearing, which is called the interference term, and that is one of the main drawbacks of Wigner-Ville distribution, right. And I should tell you that here you do not have to really set any parameters per se, that like the way you do in spectrogram. In spectrogram you have to choose a window type, window length particularly. Here there is no such choice that is required. So in that respect it is superior, and Wigner-Ville is superior in many other respects as well. But this interference term is the one that causes a headache. And then for this sine with impulse, you get very fine localization of the sine, but unfortunately the location of the impulse is lost. Okay, lost in the sense, of course you can still get it. There is a certain thresholding that I have done, that it displays only features above a certain intensity, and the intensity of the impulse is so weak that you are unable to find it. Strictly speaking, you should be able to find a contour. So that is not the main headache. The main headache is the presence of interferences, as a result of which numerous efforts have gone into improving Wigner-Ville, because the Wigner-Ville has certain nice properties. So there were efforts to retain some of the nice properties and also remove interferences. Now it turns out that you can't retain all the nice properties, you have to sacrifice one for the other, and the nice property that has to be sacrificed is the localization of energy in frequency, and that is exactly what you see here, that the localization in frequency is good. The the localization frequencies has become worse than the previous one, but the interferences have vanished. These interferences are the ones that have to go away, because then they introduce a lot of headache or artificial features in signal analysis. So that is the trade off now you can see in time frequency analysis. On the other hand, for chirps, the original Wigner-Ville distribution without any modification works beautifully. It is in fact the best suited tool for analysis of chirp like features. Now, this should tell you that you have to pick your tool based on the signal. This is the message that you should take with you. With this, we will come to a close. We come to a close for this lecture. That is, this is part 1 of the introduction. Now, you see that there is this lecture is titled numbered lecture 1.1 on the left top. That is a convention that we are going to follow. The course itself is divided into several units or modules, as you may call, and in each unit you will have different a certain number of lectures, and this is the introduction unit or module that we are looking at, and this is the first lecture in that unit, and therefore we have this lecture numbered 1.1. These are some of the references for this part of the lecture. I will give you references for each lecture towards the end, so that you are able to refer to the specific references. Of course, some of these references will run through the entire course. There are some excellent research survey articles that have been written, tutorials that have been written. I recommend that you go through them first before taking up any textbook. Of course, there are the books that I have cited are also the most widely referred books. The book by Cohen's book, for example, will serve as a good reference. The book by Mallet as well, and the book by edited by the two gentlemen there, titled the book titled Time Frequency Analysis, right, is also going to serve as a good reference for our course. And then there are some other articles from where we will draw some material. Notation is something that you have to live with. Notational differences. Each textbook, each author would like to use a certain notation, and Cohen is a physicist, so therefore there is a certain notation, whereas Mallet is an engineer, so there is certain other notation and so on. And I use a notation that is different from all the textbooks, but it is not too different. So therefore, when you read up these textbooks, please look beyond the notation and don't get bogged down by the notational differences. This is just a general word of advice. Okay, so we will meet in the next lecture. Thank you.